Hey everybody, Samuel Singer here, the founder and executive director of Wyoming Stargazing. Thanks for joining me and welcome to Mind Bending Astronomy. In every episode, we'll share with you, a mind-bending fact about astronomy. Last time we took a look at the special and general theories of relativity. We learned that gravity is the bending or warping of spacetime caused by mass moving through it. It's really impossible to visualize this because the warping happens in 4 spatial dimensions, and we can only conceptualize things in 3 spatial dimensions. However, a bowling ball rolling over a mattress provides a nice corollary to what we're talking about here. So, what does the warping of spacetime actually mean for our day-to-day experience? Well, pretty much nothing. Newton's laws of motion and his law of universal gravitation do just fine for all things here on Earth. However, when you start comparing events on Earth to events out in space, things start to get interesting. Noticing the effects of relativity requires something to relate to. One such effect is called time dilation. Observers traveling at different speeds relative to each other will measure time passing more slowly for the observer traveling more quickly. Here's a fairly simple example. Astronaut Scott Kelly spent about a year on the International Space Station, traveling at about 17,500 miles per hour for the entire time he was up there. When he returned to Earth, his twin brother, Mark Kelly, was about 5 milliseconds older than Scott, compared to when Scott left Earth a year before. So even traveling at those really fast speeds, time dilation was just barely noticeable. But what about if you're traveling close to the speed of light? Here comes the twin paradox. Let's say you have a twin brother. You hop in a spaceship and blast off from the Earth traveling just under the speed of light. For now, don't worry about the time that it took to accelerate to that speed, or the time that it takes you to slow down on your way back. You travel away from Earth for 1 year and then turn around and come back at the same speed. So for you, it took 2 years to complete that trip. However, when you return to Earth, you discover that over 200 years have passed, and you get to meet your twin brother's great-great-great-great-great-great-great-grandchildren. You may be thinking about the movie Interstellar, that depicted something similar to this. However, in the movie, it wasn't traveling at fast speeds that led to time dilation. That's relative velocity time dilation, like we just talked about. In the movie Interstellar, it was a really strong gravitational field around a fictitious black hole that led to the time dilation effects that astronauts orbiting around that hole felt compared to observers back at Earth. You see, time passes more quickly when you're in a weak gravitational field, like on Earth, compared to when you're in a really, really strong gravitational field, like around a black hole. To learn more about time dilation, click on the links that I have in the transcript of this talk. They're really great, and I think they'll help you understand both relative velocity time dilation and gravitational time dilation. Next time, we're going to explore some of the other bizarre consequences of traveling close to the speed of light. Until then, be well, and don't forget to look up.